Hey, everybody. Thanks for coming to another round of quantum computing meetup and discussion. Today we have, one of our regulars, Naden, back at Talk Again. Just speaking about Shor's algorithm with 4 topics in the agenda. First, going over unitary transformations, and then going to quantum Fourier transformations, numbers theory, and the threat to internet security. I'm sure you've already heard of Anna's background at this point, but just in case we need to go back there, she did receive her master's degree in physics at the University of California, Davis, and actually got her MD at the, I don't know how to pronounce it, but yeah, she got her MD as well. Currently, right now, she is a physicist educator at the Applied Quantum Physics Corporation, and also providing a lot of educational support on quantum computing on her website. Make sure to check that out after the meetup. And yeah, well, ladies and gentlemen, and Naden.
Thank you, Ilya. So this is about Shor's algorithm, and I'm going to start off. Shor's algorithm promises to break public key encryption when the quantum computers are available. And public key encryption is used in the entire certificate authority infrastructure. It's used in email. It's used in online credit card transactions. And it's used by the government. It's not used for bulk encryption of large amounts of data. What it's used for is transmitting the encryption key, the symmetric encryption key that is used. So if it's compromised, the game is up. And so what people are doing, I'm quite sure they're doing it, is they're recording the encrypted transmissions now. And then when the computers become available, they'll be able to read it. So Peter and Jennifer Shor, perhaps his daughter or his wife, wrote this poem. If the computers you build are quantum, then spies everywhere will want them. Our codes will all fail, and they'll read our email till we get crypto that's quantum and dantum. I'm going to paste. I pasted. I just lost my video camera fell down.
And are you good over there? Okay, we see you. Oh.
But I can't see you.
Oh.
Peekaboo, there you go. So we're getting back to Enigma, huh? Interesting.
So I talked about the importance of Shor's algorithm. The thing is, public key encryption is based on factoring products of prime numbers. And that can be done with the classical computer. It just takes a million years for the large numbers that are used. And that's why nobody's proved it, but that's why it's believed that the RSA encryption scheme is secure, at least in the pre-quantum era. So the difference between quantum factoring and factoring on a classical computer is one of what's called computational complexity. Complexity theory is based on Turing machines, and the Church-Turing thesis is all computing devices can be simulated by a Turing machine. Well, that was true until we got quantum. Another formulation, any physical quantum computing device can be simulated by a Turing machine in a number of steps, polynomial in the resources used by the computing device. So what that says is if you take the number of digits in the integer that's part of the public key, then it would, if you could do it in polynomial time, then the number of steps, the number of instruction cycles would be a polynomial, like a square or a cube of the number of digits, proportional. That's not the case for classical computers. It's only the case for quantum computers. That's Shor's algorithm. So complexity is a measure of the amount of computing resources that a particular algorithm consumes when it runs. So let's take the example of sorting through a list with n elements, searching through a list of n elements. Well, the naive strategy is to just look at them one at a time. So on the average, you'd have to go halfway through the list. So what they say is the complexity of searching an unordered list is n. Now, if you sort the list, you can use binary search where you can jump around and do it much faster. The complexity is log n, which is a function that increases much more slowly. Are there any questions or comments? Okay, well, as I've been saying, breaking public key encryption is exponential in the amount of time. Of course, exponential is like 110, 110, 100, 1,000, 10,000. It grows very fast. And on a quantum computer, it's polynomial time. And that's where the division is made between what's considered practical and what's considered impractical. So there's a lot of math in this topic, and we're going to have to look at it. The first topic is prime numbers. The prime number is well, it's kind of a generalization of odd numbers. Odd numbers can't be divided by 2. Prime numbers can't be divided by 2 or 3 or 5 or 7. They can't be divided by anything. So I've listed out the first 6 prime numbers, 2, 3, 5, 7, 11, and 13. And the fundamental theorem of arithmetic is that any integer can be expressed as a product of powers of primes. So I've shown 84 here. It's 2 squared times 3 times 7. The numbers we're dealing with public key encryption are products of only 2 primes, a pair of primes. And the name of the game is to find those primes. Now, if you find one, you can, by dividing, you can get the other one immediately. So the key concept in public key encryption is the greatest common divisor I've shown here an algorithm for computing the greatest common divisor. So take 4 and 6. The divisors of 4 are 1, 2, and 4. Well, 4 doesn't count because that's the whole number. So the divisors are 1 and 2. The divisors of 6 are 2 and 3. So what do they have in common? The common divisor is 2. Similarly, the greatest common divisor of 10 and 15, 10 is divisible by 5, and so is 15. And so the common divisor is 5. Now, what we're mainly interested in is pairs of numbers that are relatively prime. That is, they have no divisor in common. And I've given you an example here, 7 and 11. The only number that goes evenly into 7 and 11 is 1. Are there any questions or comments? So these are the complexities, the numbers of steps required to factor a semi-prime integer. A semi-prime integer, these are the ones we're concerned with. They're the products of two primes. So the best known classical algorithm is called the general number field sieve. And it's a little hard to see, but n is the size of the integer. So log n is proportional to the number of digits. So the amount of work that you have to do is exponential in the number of digits. But with a quantum computer, it's more like the square of the number of digits, and that makes it practical. Of course, you need thousands of qubits, which we don't have. So I've given you the key example that we're going to look at today, 15. It's a product of 3 and 5. So these are our secrets. 3 and 5 are our secrets. Now, it's easy to look at 15 and know that it's 3 times 5. But we're talking about numbers that are hundreds or thousands of digits long. And it's almost impossible to get the prime number, the prime factors. So here's a flow chart of Shor's algorithm. This is what you get from the public key, a semi-prime number. In our example, it's 15. You pick an integer at random that has no divisors in common with the public key. In other words, a co-prime integer. And the example we're going to deal with today is 7. You find the period, and I'll explain what that means, but we're going to get 4. And from the period, you get the factors, 3 and 5. Now, sometimes you won't get 3 and 5. You'll get 1 and 15, for example, and that's not useful. That's not the answer. So this is not really a deterministic process. You're not guaranteed to get the right answer, but you'll know if you get the wrong answer and you just repeat the computation a second time, and you'll probably succeed that time. By the way, I'm having a technical difficulty. I've lost everything. Bear with me 1 minute. The foundation for what I'm giving you today is from IBM's wonderful textbook, online textbook, the Qiskit textbook, and I've pasted a link in the chat. So to kick off Shor's algorithm, you have to have a co-prime integer, an integer that doesn't have any factors in common with the public key. So if in the example we're doing, the public key is 15 and the co-prime integers are 2, 4, 7, 8, 11, and 13. 3, 5, 6, 9, 10, and 12 are not, because they're multiples of either 3 or 5. Are there any questions about co-prime integers? So it's all based on modular arithmetic. Modular arithmetic is where you do the computation, you divide by the modulus, you divide by a number, which is a reference number, which is called the modulus, and you look at the remainder. And the remainder is what tells you whether it's equal or not. Shor's algorithm is based on finding periods. So what I've got here it says e to the x mod 35. That should be 3 to the x mod 35. X is an integer. And as you can see, if you look closely, this curve repeats. If you go from 0 to 12, it starts over. So 12 is the period. Here's the code that generated this figure. So this shows what the modulus is. You just keep subtracting the modulus until it's less than the number you until it's less than the number you started with, and that generated this figure. So it's very important to understand what I'm talking about as far as the period of a function. So if there are any questions, speak now, or, well, I won't say forever, hold your peace. Speak now or wait until the next slide.
Yeah, I guess I could just hop in there. So the period is just the remainder after you just divide it by a number?
No, the result is the remainder. The period is like 3 to the 0 is 1. 3 to
Right.
the 12 is also 1. So the period is 12.
Okay.
So let me work an example. Say x is 3. 3 cubed is 27. Well, the remainder is also 27. Let's take x equal to 4. Then 3 to the x is 81. If you divide that by 35, you get 2 with the remainder 11. And you can see right here, that's the answer. 3 to the x mod 35, or 3 to the 4th power mod 35 is 11. Does that help?
Sort of, yeah.
Or
So I have a question here. So I'm looking into the Qiskit textbook, and it's saying AR mod n is equal to 1. So A is a co-prime number that we're determining here, and it's a co-prime number less than n. And
It is, but
in
we
this
didn't
case-
determine it. We just picked it at random.
So the value 3 in this case can be any random number.
As long as it's
That is
co-prime to n. But we
Okay,
couldn't
co-prime to 35.
Yeah, we couldn't use 5, for example, or 7.
Okay. And if this number 3, for example, does not fit a solution, then we would go to the next co-prime number.
No, we could do it again with 3, actually. It's not a
Okay.
deterministic process. So, these quantum states are represented by integers, and I've shown here a 3-qubit system. So there are 8 states. You can think of this as 3 particles, 3 spinning electrons, 3 polarized photons, or just 3 qubits in a quantum computer, 3 transmons or trapped ions. Anyway, we're going to be representing, we're not going to use the representation on the left here, this one. We're going to use the representation on the right. And if you look at this, you can see it's binary encoding. It's 0, 1, 0. Well, that's binary for 2. 0, 1, 1 is binary for 3. So these are the states that we use in the quantum Fourier transform. One point that was raised in a previous seminar I gave was you think of a classical Fourier transform as like a signal processing process where you have a time series, things that are sampled in time. That's not what we have here. What we have is the states of the multi-qubit system. So here's where we get into the theory. U is a unitary operator. You can think of a unitary operator as a rotation in Hilbert space. Rotations in ordinary space preserve length. So if I take a car and I turn it upside down, that's not going to change the length of the car. Likewise, rotations in Hilbert space, unitary transformations, preserve the complex norm. It's a generalization of the concept of the length of a vector. It's where you take the magnitude of each component and square it and add up all the squares, and then you take the square root. That's the complex norm. And unitary operations preserve the complex norm, and there's an inner product. It's analogous to the dot product between 2 vectors, and they preserve that too. Are there any questions about what is a unitary matrix, unitary operator? So here we dove into abstractions. But A is 3 in this example. Y is the quantum state. It's the right-hand column here, 0 through 7. If there were 3 qubits, in the example we're going to do, there are more than 3. And so if you multiply times 3 and then take the remainder, that's what the modulus does. Well, 3 times 1 is 3. 3 squared times 1 is 9. 3 cubed times 1 is 27. take my word for it, 3 to the 11th power leaves a remainder of 12. 3 to the 12th power gets you back to 1. So it's periodic, it repeats. And the way Shor's algorithm works is it finds the period of the unitary transformation. Now, I promised you that this runs in polynomial time, that it doesn't take an exponential number of steps. Can anybody look at this slide and see why I've kind of violated that requirement? Well, it's because I have powers. So you might have well, I'll illustrate it in a moment. But you have to say you wanted to take 7 to the power 560 modulo 561. You'd have to multiply 7 560 times. Well, that's too large. That's inefficient. So there's a shortcut. I've given the pseudocode here. I'm not going to walk through it because I haven't mastered it. But as you can see, rather than 560 steps, you have only 10. So that's a key part of Shor's algorithm. And this is done on a classic computer. So this is the first implementations of Shor's algorithm are going to be hybrid, where the Fourier transform and the period finding is done on a quantum computer, and the rest of the computation is done on a classical machine. In a moment, I'm going to show you the quantum circuit that does this job. And the very first quantum circuits are made of gates. You can think of a gate as like an instruction in the instruction set of a classical computer. It's a single step that can't be divided into parts. And the first gate we're going to use is the Hadamard gate. And to explain the Hadamard gate, this is called the block sphere. It's a way of visualizing qubits. So qubit 0 is at the North Pole. Qubit 1 is at the South Pole. But you might be on the equator as well, like here, which is X. What the Hadamard gate does, what all gates do is they rotate the vector in the block sphere. And the Hadamard gate rotates it about the y-axis. So it brings it down here like this, 90 degrees. So it takes 0 to x. It takes 1, it rotates it again about the y-axis, 90 degrees. So that brings it up here, which is minus x. Are there any questions?
The question, the Hadamard gate, it retains the information from the either ket 0 or ket 1. And so from ket 0 is going to be on positive x.
Yes, it takes ket 0 to positive x.
Okay.
Hey, Anna, Jerry was just wondering if that was entanglement.
It's not, because we only have 1 qubit. An entanglement takes 2. It's like dancing.
True.
I wondered about that. Like the Qiskit textbook that I referenced they show multiple qubits as a set of block spheres. Now, my understanding is you can't do that. Actually, you can do it if they're not entangled. And so what I concluded from this, and from the fact that they use these block sphere illustrations for multiple qubits, is that entanglement, as near as I can see, is not part of the story for Shor's algorithm. I hope what I'm saying is true, but that's what it seems to be the case. And you can kind of see the same thing here in the quantum circuit. No, I was wrong. We do have entanglement. No, we don't, because we don't have a control NOT gate. Well, I'm going to stop guessing at this point. This is the quantum circuit that is the fundamental part of the Shor's algorithm. You have a bunch of zeros. Each horizontal line is 1 qubit. Okay. We apply the Hadamard gate, and this is a controlled operation. So that if we had a 0 here, then this unitary operator would not act. The state would just pass through unchanged. If we had a 1 here, the unitary operator, which is multiplying by a raised to a power, would take effect if we had a 1 here. Now, with the Hadamard gate, we've got a superposition of 0 and 1. So we actually get a combination of 2 scenarios, one where the gate runs and one where the gate doesn't run. So this is the circuit. I'm not sure what you're all seeing right now, but yeah, I've lost the slideshow, haven't I?
Yeah, we're not seeing anything at all.
U is the unitary operator that takes the quantum state and multiplies it by A.
So Rajiv had a question, Anna. How do you create and write the code for you?
I don't have a slide for that. It's in the textbook. It involves a number of swap gates. And this black box right here is the quantum Fourier transform. And what we're doing here is we're estimating the phase. See, every unitary operator preserves the norm. It preserves the magnitude of the vector. And what that says, if you look at the complex numbers, is that it merely applies a phase factor. And so the whole game for Shor's algorithm is to find that phase. And what is phase? I've illustrated phase here. I've got two waves, two sine waves. Well, supposing we perform these measurements and we get 1 and 0 and 1, that's a 7. I'm talking in a 3-qubit space, so that'd be 2 times pi times 7 over 8, 315 degrees. I made an error here. I divided by 16. Should have divided by 8. Here's a 157-degree phase shift. It actually should be twice this long. Here's the greatest common divisor algorithm again, because we're going to need it. So now we get to the finish line. We've got to extract the prime factors from the phase. Now, a quantum computer doesn't just give you one answer. It gives you a set of answers, each one with its own probability. And in this case, we got 4 answers. Um, 0, 0, 0, 0, 1, 0, 1, 1, 0, and 1, 0, 0. So that gives you 0 divided by 1. The next result gives you 1 divided by 4, then 3 divided by 4, and 1 divided by 2. What this is actually is 2 divided by 4. These numbers aren't co-prime. They have the factor 2 in common. So if this is the result we got, then we'd have to repeat the computation. We wouldn't have to change any of the conditions. We just run the calculation again, because quantum mechanics is probabilistic. So how do we get the factors? Well, the period is 4. So that says 7 to the 4th power has a remainder of 1, which says that 7 to the 4th power minus 1 has a remainder of 0. That is 7 to the 4th power minus 1 is a multiple of 15. Using high school algebra, you can factor this expression into 2 factors. And these are what are going to give us our answer. So the greatest common divisor of 7 squared minus 1 with 15 is 3. The greatest common divisor of 7 squared plus 1 with 15 is 5. So we got our factors and we succeeded. Are there any questions or comments?
Yeah, so this part here, this would be done like finding the greatest common factor. This would be done in like a classical computer, right?
The phase, getting the phase is what's done on the quantum computer.
Yeah. So once the phase is found, you just find the greatest common factor just using a regular computer. And then if they say that it's a failure, you run it on the quantum computer again to find new phases.
Yep.
Okay. And you just run through that multiple times until you get to prime factors, like prime numbers.
Mhm.
Okay.
And you won't have to do it very many times.
Sure.
Hey, Anna,
Yeah.
a couple slides back. Oh, we lost your slides. You were showing the circuit for Shor's algorithm. In the lower left corner, you had the ket psi. Yeah, there you go. And then is that actually a quantum register that forms the ancillary bits? Or is it the same size as the normal register or the top register?
So the question is, what is psi, right?
Yeah.
Um,
And the reason I'm asking, because I've seen some of these explanations in different packages where the ancillary bit is just is another register. And so I'm not sure if that's what the notation, the exponents on the U are. It's indicating that it's operating in a certain subset of that register.
no, the exponents, right, T, let me get my pointer. T selects which qubit you're working with, 0, 1, 2, 3, and so on, I think. And what psi, I believe psi comes from that random number that we chose, the coprime number, the A, the 3.
Yeah, okay, so it has to be more than one qubit to hold that
Yes.
number then, right? Okay, all right, good, thanks.
So finally, these are all my slides, but I realize I haven't really shown the Fourier transform. So I'm going to bring that up. I have another PowerPoint presentation. So this is a classical Fourier transform. I've just dummied up a signal here with 3 frequencies in it. And when I compute the Fourier transform, I get spikes according to the period of the function. Now, the way this is different from the quantum case is this is a time series. These are measurements that are performed over time. Whereas with Shor's algorithm, you're dealing with multiple qubits. This is the definition of the Fourier transform. And it's the same for quantum as it is for classical.
But would you ever have to apply the Fourier transform on a classical computer?
No, you wouldn't. With the math you use to define the circuit is the same as the math that's used to derive the fast Fourier transform that's used on classical computers. The algebra is the same. That's why I'm bringing it in.
Sure.
So,
Professor, the question here is where is the optimization performed? Is it in the QFT for the Shor's algorithm?
I don't see optimization as really being part of the story here. I could be mistaken, but I'm not aware of it. Here's the quantum definition of a Fourier transform. This is the sum over all the possible states of the multi-qubit system. This number here is very interesting, and you should try to focus on this if you want to understand the algorithm. This is a phase factor. It's a complex number whose norm, whose magnitude is 1, and whose phase is different for each quantum state.
So I guess that's like the gist of it, right? Like the Fourier transform. So in that graph above, you showed like what was going on with like a certain qubit over a time period. And then the transform literally just takes that graph and just converts it into the number of like frequency. So the number of times something has come up multiple times during that time sequence.
It's the inverse of the period, the inverse of the separation that you have to for the sequence to repeat itself.
Okay, I see.
So if you do the math, you can rewrite the definition like this. And these 0.j, these are like binary fractions. So like 0.1 represents a half, 0.11 represents 3/4, 0.01 represents 1/4, 0.001 represents 1/8, and so on. So if you go through these manipulations, you start off with the fundamental definition of the Fourier transform, and you just do the algebra. And this is what you get. And the value of this expression here at the end is that you can write a circuit, a quantum circuit.
And all of this is going on in the circuit that you showed us, you know, with the block that said QFT.
Yep,
Yeah, that's just going on in there, right?
yep.
Yeah.
So here's the circuit, the Fourier transform circuit. So you get, there's a good animation. I'll show it in a moment. That shows that you're on the equator of the block sphere. So you have equal parts 0 and 1, but with a phase shift between the two. So this is your Fourier transform.
So I guess just a follow-up question is like, do you have to apply a Fourier transform to every kind of quantum algorithm or just Shor's algorithm?
There are others.
Okay.
And that phase estimation is apparently fundamental for a large number of algorithms, but I couldn't tell you which ones.
True.
So that completes the formal part of the presentation. I want to tell you a story. About 4 or 5 years ago, I had a meetup group, New Chicago Quantum Computing Meetup. It was in person. And I offered to present Shor's algorithm, and I made my best effort to prepare a set of slides, and I distributed them to all my members, and nobody came. because it was so intimidating. But this weekend, I found IBM's Qiskit textbook, which explained it all with examples, this example that we worked through, and it was very helpful. I understand that IBM is offering a certification in Qiskit based on that textbook. And what I propose to do is to offer a course, a certification course on quantum computing based on this textbook, and Shor's algorithm and the Fourier transform will be part of it. So with that, I'll turn it over to you for questions and comments.
Yeah, did anyone have any questions or comments? Try to keep it related to the presentation, obviously. But yeah, if you had a question, just drop in the chat, or if you just want to go unmute yourself, just fire away.
I would just like to add, for anybody that's listening, it's really easy to run on Qiskit. All you have to do is find the right pages, and it's like 2 clicks. You go to Shor's algorithm. Actually, it's some part of Shor's algorithm. It sends you into the composer mode, and then you click again to your hardware of choice. It's free if it's lower qubits. It's not that hard.
No,
So,
it's not.
yeah, and it's free service for. I usually run on Nairobi, which is 7. And you can do circuit composer for how many qubits you want. It's totally up to you, but it's just takes time, but it's not too hard.
Thank you, Kevin.
There's a very clear explanation, I thought, Anna. And I like it's actually clearer than Shor's original paper, the example that you went through. Shor's original paper was a little dense to get to actually find out what you were doing at the end, and the example that I read about where they did this on one of the IBM computers is the fact that it was so noisy they only found one of the factors. They were factoring 21 and they found 3, but they couldn't find 7. When they ran the estimation, 7 failed because it was too noisy to evaluate the whole circuit. But what was interesting is that they then ran another circuit to measure the noise that was introduced by the quantum circuit of that volume, and then use that to subtract it out of the histogram data. So by doing that, you sort of leveled it back down, and then you could look at the differences to see which ones would work and which bits were the right answer or which values were the right answer of the qubits versus which ones were the less likely. And it was interesting to see that, but it still couldn't work even with the error cancellation that they were running, noise subtraction. It still didn't provide a definitive answer for 7. 3 was clear, but 7 was not.
There's another poem about that. Read our email, how mean of the spies in their quantum machine. Be comforted though they do not yet know how to factorize 12 or 15. Regarding Shor's paper, I looked at it this weekend. I was going to base my presentation on it, and I couldn't get through it.
Agreed. It's a little dense.
There is a link to it in the slide deck, which Helen will provide to you.
Yeah, and I had a question. Have you tried just using ChatGPT to just write you Shor's algorithm code and just run that or anything? have you
I have not yet summoned up the courage to face ChatGPT.
Right, because yeah, I feel like
I'm told that it doesn't write the best code.
I'm sure it won't write you a complex code, but it just gives you probably the basics, and then obviously you would have to understand the algorithm to kind of like edit it out, but right, true. Someone's looking into it apparently. And my second question was, so the only reason why Shor's algorithm runs in polynomial time versus the classical, which is exponential based on the number of obviously complexity, like the numbers, is because of the fact that you're using the quantum Fourier transform to find the
Period.
the period, and then you just find the greatest common factor do like classical. Yeah. Okay.
Yeah, Young, it's based on superposition, where you sort of go down multiple paths at the same time.
Right. It's just like crazy because like obviously the quantum space is all mathematics based. And it's just like, wow, like this it's crazy. But yeah. Rajiv had a question. Can you explain how superposition speeds up finding the period?
I just claimed that it did, didn't I? It's based on interference. You have each qubit in the circuit, each of those horizontal lines has a different phase. And when the qubits get combined, you get constructive and destructive interference, similar to what you get with a double slit experiment with photons. So that basically, when you've got the period right, all the phases are in agreement with one another, and so you get constructive interference. If you don't have the right period, then it's like noise. They cancel one another out because they're all pointing in different directions.
True. And a follow-up question, well, it was an earlier question actually from Rajiv. Does the quantum computer evaluate all the remainders at once to find the phase, and that's what makes it faster than a classical computer?
I think it does. I think that's what that U gate does, is it gets the remainders.
Right. Okay. And then Martin asks, when do you think quantum computers using Shor's algorithms will be able to break RSA encryption?
Last week, somebody asked me if I thought room temperature quantum computers were possible. This question is in a league with that one. I think the most promising prospect is trapped neutral atoms in an optical lattice where you have lasers, counter-propagating lasers, and the light waves form beats so that there are peaks and valleys in the force, and you trap the neutral atoms. And if you could have something that was, say, 100 on a side, that would give you 1,000,000 qubits, and you could factor, you could break encryption. So I think it'll be, well, I don't know when it'll be, but I'm 72 years old and I expect to see it in my lifetime.
I guess to just follow up on that as well, like I'm assuming like RSA encryption factors, like 2 factors, are like super large, right? So like
They are.
probably like in the billions. So like going back to your point where you showed the 3 qubits that represents 0 to 7, you would need all the qubits to represent that number, right? Like the size of that number.
The number of qubits you would need would be like the logarithm of the size of the factor or of the product of the 2 factors.
Right. And it's a logarithm because 1 extra qubit at like the 100th like can just add much more value than like the first 3 or something.
Well, like 10 qubits will give you 1,024 states,
Yeah,
because you can have 0 or 1 for each qubit. So you get 2 to the 10th power.
I see. Okay, well, that kind of answered the other question. Was someone was asking, are all levels of businesses and securities threatened once a quantum computer is set to work?
Well, the National Institute of Standards held a competition over the past several years for post-quantum cryptography, and they have algorithms which are supposedly quantum safe. The problem is, in the meantime, they could be recording our transmissions, and it will not be safe, because once they get the quantum computer, they can read it.
True.
One question. Uh,
Yeah.
so how does one go about, I don't know if it is the right time or the right question, but how does one go about, so you have an objective in mind, how does one go about from creating the algorithm to going down all the way to the gates? Why haven't the gates been abstracted out in terms of more higher level usage functions or whatever, right? So why do we have to go down to the level of circuits? Is there a way to simplify this whole thing in terms of, okay, I have an objective, now I need an algorithm, now I need to go all the way down to the circuits, building the
So your
gates.
question is, why do we have to break it down into individual gates? Why can't we analyze it from a higher level? Is that right?
Yes, if I may ask that way, I don't know. Yeah.
Well, it's a legitimate question, and people are working on it. The Silk language is a higher level language for programming quantum computers, but it hasn't been accepted. It's not successful yet. It's a hard problem. So we're stuck with the gates for now.
Thank you.
If you're looking to do more things, there's a company called Classic with a Q. I would definitely check them out. They try to make it easy on you, so you don't have to hire as many programmers, those types of things. I talked to CEO and he said that you have to have technical people to interact with Classic, but it's not to the point where it's just like, just CEO says like higher level, I want this done, and then you tell them. So at this point, yeah, you need to have some technical expertise, it looks like.
No, I'm okay with the technical expertise. I'm ready to code in Python, which I do on a regular basis. But the question is, how do you translate? I mean, probably I've not dealt in depth with quantum. I'm just starting off on this topic. But how do you translate the higher level objectives all the way down to the gates? Probably is the way I should ask the question.
My opinion is that's an unsolved problem. We simply don't know much about quantum algorithms. Quantum algorithms are very hard to design because they require us to think in ways that are not familiar from everyday life. We have to think in the quantum world, and most of us have to rely on complex mathematics to do it. So that I'm not an expert on quantum algorithms by any stretch of the imagination, but my impression is that the landscape of quantum algorithms is not well understood. Like, take Nielsen and Schwann, the textbook. It focuses on a very small number of algorithms that are well understood, and the rest of them don't get much attention. Maybe they're not useful, maybe they're not understood. So to translate a set of high-level requirements into a quantum algorithm, I just don't think we're there yet. I don't think we have even an approach to that. I don't know, maybe Kevin, you've heard something different.
Yeah, it's being tracked. There's two articles. There's a Los Alamos National Lab article, Challenges and Opportunities of Quantum Machine Learning. So that can kind of steer you into, if it's supervised learning. I don't think as much with reinforced. And then there's another one, it's the Big Table of Quantum Artificial Intelligence. So this one has been going on, I think, since like 94. And then it's the whole CC, CQ, QC, QQ kind of thing. You have data, algorithms. But, some of it you just have to read. And I would say it just depends on your data at that point. And then, a lot of it's in literature. You just have to find it.
So one of the issues with quantum is you don't, if you're thinking of an algorithm, based on your experience with classic computers, you don't just take that algorithm and take it over to quantum and run it. The first step in pretty much every text I've ever been through so far talks about you got to restate your problem into a form that quantum can solve. So that's a huge leap right there. So and that's really where a lot of the magic happens. Like in this presentation, and I hope Anna can speak to this a little bit. They in this presentation referred to the quantum Fourier transform, but in effect, and I've seen different presentations on this. It's actually the inverse quantum Fourier transform that's being used, and it's being used in a different way from what classical does. We're not taking time-based information and turning it into coefficients and phases of frequencies. We are using the inverse Fourier to find a period. This is what I've seen, and again, so I'd ask Anna if she could comment on that, or if you can comment on that.
I think you hit the nail on the head, Ron.
Yeah, so I mean, it's people have to be prepared to make that paradigm shift. You don't go into quantum to write accounting programs. You're going to go there to solve, and you have to restate your problem in something that quantum is good at solving.
Fair enough. So the way I'm looking at it, is there a framework which people can employ? Has it been written up? Is there any academic papers, for example, which talks about a framework which needs to be employed mentally in order to move from the classical aspects to the quantum aspects?
Yeah, I mean, if you're talking like convolutional neural nets, or in this case, quantum, they call them quantum convolutional neural nets or convolutional. They say, I just watched a YouTube, I think it was Xanadu. It was 2 years old, but it's just a toy. You'll find a lot in these medical kind of imaging papers, quantum being used for state preparation and measurement. And then the bulk of it, as far as I know, and this probably applies to other papers, is still being used classical for pre-post processing, the actual learning, training, testing, those types of things. It's getting over that hurdle with the noise and the number of qubits. We're still promised that it's the NSF's practical quantum computer this year. So I'm banking some things off that. And then say, for instance, INQ has a manufacturing facility coming up first half of next year. So good stuff in store.
Sorry, I'm just gonna, Anna, do you want to, yeah.
I think, Krishna, the real issue as far as having a general conceptual framework for mapping a problem onto a quantum algorithm, the real issue is quantum mechanics is not really understood. I mean, we're able to make predictions. If you give me a circuit, I can turn the crank and tell you what's going to come out, but that's not the same as understanding. If I try to explain what quantum measurement really is about, I can't give you a good explanation. They're still arguing about it. John Bell's work was sort of a no-go result, where he proved that certain concepts would not work, but nobody has really come up with the concepts that do work for reasoning about quantum computers. I mean, looking at Nielsen and Swan, it's just a huge zoo of special cases and examples. And we simply don't know. We simply don't have a good handle on quantum computing yet, in my opinion.
Yeah, so I guess I had a follow-up question to that. So obviously, like right now, the state of the quantum computing industry, like we're all rushing towards working hardware. But like once the hardware is like set up and ready to go, like I feel like the value is really in people developing these algorithms and commercializing it for like market usage, right?
Yep.
Yeah. So like it really is just like but then most of the research right now is done in public institute, like like universities, research centers. So I'm just seeing like it's already like private that's going in, like private research that's going into this at all. Like I guess Google and stuff like that are, but true.
Yeah, it started in the government. So in the early 1980s, so NSF started to fund it, the research projects for, the math and all this stuff. And they still put in, I think, $800 million a year this year, the past 2 years. And a lot of these technologies, transmon qubits or superconducting qubits, ion trap, neutral atom, photonics, are actually government projects that they need help innovating. So that's where PsiQuantum, IBM, the list goes on and on. So it's really an interchange. And I think DARPA just did with PsiQuantum and neutral atom, I want to say. And then whereas IBM and INQ might be clicking a little bit more. So yeah, it's definitely an interplay, government, industry, academia. There's lots of reports on that.
So I guess Anna, like my follow-up question is like obviously like unless you're like a PhD candidate with a strong background in complex mathematics, like you're not going to develop your own like quantum algorithm, right? So like I guess for most people out there, it's kind of just like optimizing the code, like optimizing the circuit, so it uses less qubit noise, less noise, stuff like that.
Well, error correction is certainly a big issue for the
Right.
future of quantum computers.
But is that just going to be mitigated in the future by just better hardware?
I think maybe we're going to have a new kind of qubit. I read last year about qubits that are based on a single electron floating over a surface of frozen neon, and it was very pure. It had very little noise. But how do you scale it up? How do you get 100 or 1,000 of
Right.
those? I don't know.
And I guess that just like comes down to the code, I guess, right? Just developing the right circuit. It's not like mathematics. It's more
I
like
think it's a hardware issue.
right. Cool.
The challenge is these qubits have to be sensitive to one another. They have to respond to one another. You can't have every qubit shielded, but at the same time, they can't respond to the environment, which is trying to destroy their quantum state. So you've got conflicting requirements. You've got a requirement for isolation, and you've got a requirement for control and sensitivity. And these two requirements are in conflict, and that's why we have the problems we have today.
True. Yeah, it's just like I feel like everyone talks about quantum computing like it's a hardware play, but like I really feel it's an intellectual property play, right? Like
Yes.
I feel like that's how it's going to be commercialized in the future. Like I don't know, like do you see hardware being like a major hurdle within do you see like hardware being resolved in like 5 years?
Maybe not.
Yeah, it's real interesting how many quantum papers are hiding behind paywalls.
Right.
But you're bringing up a good point, right? Which is, so the hardware is just the hardware. They're trying to make it better, error corrections better, blah, blah, blah. But eventually, the benefit, the supreme benefit out of all this is the algorithms and how people are able to use it to solve problems. So, I mean, like, ultimately, it has to come down to that level, right? And I'm saying, like, I mean, so we haven't, so I know we are working on the hardware parts, etc. But the next step is I feel that nobody is spending enough time on the next step, which is utilizing the hardware to solve the problems. Am I stating it wrong?
Well, they all try to get together. So there's an organization called QEDC, or Quantum Economic Development Consortium. It's based off of NIST funding. It came from like a presidential funding. And they try to get together. So you can actually join their public forums, and it's kind of like they're stuck with their individual hardware. And then, you know, they do talk to each other. I really don't think it's a secluded kind of thing. And if you look back in history, say the Homebrew Computer Club, it's the same kind of thing, that they got together after work at bars and restaurants, and they said, let's figure out the personal computer.
Yeah, Anna, Rafat had a long question. Where did I even start? So I'll just read the whole thing. From what I understand, QC, you have to find. Oh, sorry.
Yeah, so basically what I'm asking is, how do we determine the quantum time complexity compared to classical?
Well, it's like the number of qubits times the depth. It's the number of gates. Well, no, it's just the depth going from left to right. How many gates are involved? And we had powers of U.
Terrible, José. No, no, todavía no.
Hey, Fernando, yeah, I'm just gonna mute you. Okay. Sorry, he was just on the phone. I think he had muted himself. Did anyone have any other questions or just general questions? Just waiting in the chat.
What's your next step, Anna? Where are you going to go after this? Because you always have some idea brewing. I mean, you got the course that you're thinking about doing. I'm interested in hearing about that. And so that'd be good.
Well,
Okay.
I've got a meetup coming up where I'm going to talk about physics for a change, using lasers to trap and manipulate atoms and ions. That's coming up in, I think, a couple of weeks. And
is that through this group too?
No, that's through the Quantum Physics Corporation.
Okay, I'll look for that.
Cool. Well, if no one has any more questions, Anna, if you have anything last to say, I guess we could wrap up.
Well, it's been fun.
Sunday night.
Thank you for joining me.
Yeah. Anna, thanks for coming once again. Always insightful discussions are always very interesting. I know it's like, mathematics is definitely hard to explain. So thank you for taking the time for you to, teach us all the complexity of mathematics. But yeah, a bunch of people said, thank you. A lot of thumbs up. Solid meetup. Yeah. Thanks for coming in.
Okay. Good night, all.
Thanks, Anna.
Yeah. Have a good night, everybody. Peace.